All right, we've looked at graphing before. Today we're going to look at graphs of families and functions. We're in particular going to spend our time on 3 functions. We're going to spend our time on our absolute value function, which we've worked with. We're going to spend some time on the x squared function, which we've worked with. And the one that we've spent some time on but not for graphing yet, we're going to work with is the square root function. Those are our 3 functions. So when it talks about families of functions, that's what it's talking about. All of our functions are going to be of one of those 3 varieties, okay? When we graphed before, what we talked about is that we can get a pretty good idea of what the graph looks like if we plot 5 points. When we had lines, we only needed a couple points, right? But when we had other graphs, 3 points wasn't enough. 2 points wasn't enough. We needed about 5. We do need to be a little careful on how we choose those 5 points. That's going to be the trickiest part of today, is how we choose those points well. And in some cases, 3 points is enough. So what cases am I talking about? Well, I'm going to talk about square roots as being those some cases for our discussion today. So when we do square root graphs, we don't need 5 points. 3 will be enough. When we talked, I think it was yesterday, maybe it was 2 days ago, but I think it was yesterday, we talked about the fact that sometimes we get answers of 0 and at some point in the middle of a problem, and that might lead us to a conclusion that's not really accurate, like deciding if something's a function. You guys know what I'm talking about? I was randomly having you guess, and every time you did, I was like, oh, that wasn't a good random guess, which, isn't really very friendly of me either, because there are some random guesses that just aren't good guesses. Okay, so we're going to focus today, when we choose our points well, at finding that place where we get a 0. We want that value because it's going to help us with our graph. So let's take a look at an example. This is an absolute value example. F of x equals 6 times the absolute value of x, and then the minus 4 is after the absolute value. And we're going to make an ordered pair chart. And we're going to have 5 values, 1, 2, 3, 4, 5. And as awkward maybe as it feels to do so, we're going to choose the 3rd value first, the middle value. The middle value is going to be whatever makes the absolute value equal to 0. So in this case, it's 0. If x is 0, the absolute value portion of this disappears, right? Okay, cool. So if the absolute value disappears, what will the y value be? Yeah, the negative 4 that's at the end. Okay, is everybody okay with what I chose? Does that make sense? As you see another example, you'll understand more about why this one felt like I didn't really do anything. It felt weird, but it's sometimes more strategic than that. What you're going to do next is you're going to go 1 up and 1 down from 0. So 1 up from 0 would be 1, 1 down would be negative 1. And you're going to go 1 up and then 1 down from that. So 1 up from 1 is 2, 1 down from that's negative 2. Negative 2, negative 1, 0, 1, and 2. Those are actually the same 5 points when we were starting before, because this one's very friendly. So we're going to plug in the points one at a time and evaluate them now. So if I plug in a negative 2, so 6, times the absolute value of negative 2, and then minus 4. Well, what's the absolute value of negative 2? 2 times 6 is 12. 12 minus 4 is 8. So the first point has a y value of 8. We're going to go through all of them this way. Negative 1. Absolute value of negative 1 is 1 times 6 is 6 minus 4 is 2. And if we've chosen well, those numbers will be the same numbers we get on the bottom half of this list of numbers. So let's check just to make sure that you see what I mean. Let's choose the number 1. What's the absolute value of 1? 1 times 6, 6 minus 4 is 2. Did I duplicate a number? I did. And 2 will work the same way. Oops, I should have had a minus 4 there. Absolute value of 2 is 2 times 6, 12, minus 4, 8. So when I say that we're choosing well, what I mean is I want to choose so that I see symmetry happening. The top half, the first two values, are the same if I flipped them to the bottom. And we're going to plot them. So as I plot these points, -2, 8, -1, 2. I had, oh, I didn't get it written down, did I? 0, -4. 1, 2, and 2, 8. Any guess what kind of shape I'm getting? Use a good guess. It's not a U. V. Absolute value graphs always look like a V. Okay? So, if I connect them, whoa, let me try that with the line. How about a solid line? That's better. This would be my graph. It's a V. An absolute value should always look like a V. Let's try another one, and you'll see how strategically choosing the points becomes maybe a little less intuitive. Okay. What point, what x value, is going to make the absolute value 0? Yeah, if x is -6, I would get 0 inside, right? Did everybody see that? So my middle value here is going to be -6. And then I'm going to go up 1 to -5 and up 1 to -4. That's adding 1. And I'm going to go down 1 to -7 and down 1 to -8. These are going to be my 5 well-chosen points. Now, I chose the middle one on purpose because it made this whole piece 0, right? And then if I take 0 times -5, I stick with 0 on this one. So it's not always a 0 y value. The last one wasn't, but this one is at the middle value. All right, so let's see what happens now when I plug in the values 1 bigger and 1 smaller. So if I plug in 1 bigger would be -5. What is -5 plus 6? 1. Absolute value of 1 is 1 times -5 is -5. And if I plug in the number 1 smaller, so 1 smaller would be -7. What's -7 plus 6? -1. And the absolute value of -1 is 1 times -5. It's -5. The symmetry is happening, right? Because we chose well. Now let's go 2 bigger. What if I used a -4 here? What is -4 plus 6? 2. Absolute value of 2 is 2. Times -5 is -10. And if I do 2 smaller, I'd have the -8. -8 plus 6 is -2. Absolute value of -2 is 2. Times -5 is -10. Okay, symmetry's going good and strong, and we're all good with that. And now we get to plot the points. -8, 10. -7 and 5, -6, 0, -5, 5, and -4, 10. And, oh, I'm sorry, those were negatives and I plotted them as positives. Let me flip that upside down. I'm sorry about that. -8 and -10. -7, -5. There we go. All right, very good. It's still the shape of a V, it's just upside down. And we'll talk more later about why that's the case, but does anyone have any guess looking at the equation of why it flipped upside down? It's the negative in front of the 5. That's why it did it. Yeah, we'll look more at that next class period. Okay, so these are absolute values. Squares. We've looked at squared graphs. So again, my goal is that the squared term becomes 0. So on this first one, it's very nice to choose. What is the x value that makes the squared term become 0? 0, right? If x is 0, x squared is 0. And 3 times 0 is 0, so the y value there is also 0. And we go up 1 and down 1 from that. So up 1 and down 1 to get the other 2 points. So let's try it. If I plug in the number 1, what is 1 squared? 1 times 3 is 3. But what happens when I plug in negative 1? What is negative 1 squared? 1 times 3 is 3. Do you see the symmetry? How about negative 2 and positive 2? Let's see. What is 2 squared? 4 times 3? 12. Good job. So there's a 12 down here. And what if it's negative 2? What is negative 2 squared? Close. 4. Yeah, so negative 2 squared is positive, and then it's 4, just like the other one was. It's 4. And 4 times 3 is 12. Is there symmetry? You bet. So let's plot those. Negative 2, 12. I don't have a 12 on my graph, so I'm going to have to extend my line up here. Sorry about that. Negative 2, 12. Negative 1, 3. 0, 0. 1, 3. And 2, 12. It kind of looks like a V. But if you tried to connect it with straight lines and you were drawing it very well, like accurately, the straight lines won't connect. They won't hit those 3 dots on the right and the 3 dots on the left. Because when you have an x squared graph, it isn't a V. What shape is it? It's a U. So this shape needs to look smooth instead of rigid. And it looks something like that. It is a U shape. All right, our next example, we have to choose a little bit more strategically, kind of like my second example before. I need the value that will make the squaring part, this piece, equal to 0. What x value will give me a 0 inside of my circle? What would x have to equal? Somebody said it. 1. Thank you, Lauren. Yeah. If x is 1, the part that's inside my circle right now would be 0, right? So let's check it. If I did 1 minus 1, do I get 0? Yeah. What's 0 squared? 0. And then minus 3 would give me the negative 3. And we're going to go up and down 1 from this. So if I go up 1, I have 2. Up again, I have 3. Down 1, I have 0. Down again, I have negative 1. So let's try them. Let's try 2. What is 2 minus 1? 1. 1 squared is 1. And then 1 minus 3 is negative 2. How about 0? What is 0 minus 1? Negative 1. But what's negative 1 squared? 1. It's positive again, right? 1. And 1 minus 3 is 2, negative 2 rather. Do you see the symmetry? Good. Symmetry should be happening either, if it's not, you've either made an error in your calculation or an error in the choice of your points. So let's try the next values. The next values are supposed to be 3 and negative 1. So what is 3 minus 1? 2. 2 squared is 4, and then 4 minus 3 would be 1. The other one's negative 1. What is negative 1 minus 1? Negative 2. Negative 2 squared is 4, and 4 minus 3 is 1. If you don't like doing all the nitpicky little evaluations that I keep saying out loud, your calculator's right there. Use it, it's fine. Let's plot the points. I have negative 1, 1. We have 0, negative 2. 1, negative 3. 2, negative 3. And then 3, 1. Does it look like a U? It does. And we'll connect them. Okay, so we've done absolute value graphs. We've done squared graphs. What's the third type of graph I was telling you we were going to do? Square roots. So let's do a square root one. And on these, we only need 3 points. Put yourself a little note right here. 3 is enough. Again, they have to be 3 well-chosen points. 3 arbitrary points is not going to be useful, but 3 well-chosen points will be enough. Okay, so the first well-chosen point is just like it was happening with the other values. What we want is we want to make whatever underneath here 0. What x value would make the underneath part of that radical 0? 1. Good job. So if x is 1, it's a 0 underneath the radical. So then if I had the square root of 1 minus 1, so 1 minus 1 is 0. What's the square root of 0? 0. We actually talked about that one when we were doing homework stuff today, right? And then we're going to go up 1 from that value. So the 2 will work. So let's try that one. What is 2 minus 1? 1. And what's the square root of 1? 1. That's very friendly. So those are very prescriptive, right? I can tell you exactly what to pick. The next one is a little bit less like that. I'd really like to take the square root of something I know. I like the square root of 1. What's the other thing I would like to take a square root of? 4 would be nice. What's the square root of 4? The square of 4 is 16. What's the square root of 4? 2, right? If I could somehow get the square root of 4, I would know that the answer is 2. Or if you really don't want 4, you would do square root of 9. That'd be great. That'd be 3. We'd like to take a square root of something that we actually have a whole number for. It'd be nice. So I'd really like to have this one just because it's the smaller of the two. Square root of 4 is 2. But look at the comparison here. What x value would make that happen? 5. You found it really quick. I'd like to make that happen. So I'm looking for where the value underneath the radical would equal the 4, and that would be at 5. So if indeed x equals 5, I would have the square root of 5 minus 1. 5 minus 1 is 4, and the square root of 4 is 2. So let's plot those 3 points, and I'll talk to you as well about why 3 points is enough. Here's 1, 0. 2, 1, and 5, 2. Looks like this when they're connected. It is it's not a line, it's smooth. So considering that curvature right there, it should look like something else we've done. It should look like half of a parabola on its side. That's not an accident. We'll talk about why that happens when we get to Tuesday, I believe it is next week. But But that's why 3 points is enough, is because it's half the points, right? Including this corner point. It's got a name, it's called a vertex. But including that point, it would be half of the other number of points. That's why it's enough. Last example, and we'll stop for today. Same idea. My first point I want to choose what makes the underneath of the radical equal to 0. So what number would that be? It would be negative 3. What is negative 3 plus 3? 0. Square root of 0 is 0. Plus 1 is 1. The next value is 1 bigger. What's 1 bigger than negative 3? Negative 2, right? What is negative 2 plus 3? 1. What's the square root of 1? 1. And what's 1 plus 1 at the end? 2. Now, the next value I want, what I really want is I want it to have a 4 underneath here when I'm done. So looking at this piece right here, what number would I have to put in so that x would have to be 1, right? If x is 1, then everything underneath the radical would be equal to 4. You guys with me on that? So if I had a 1 plus my 3, I'd have 4. The square root of 4 is 2. And 2 plus the 1 at the end would be 3. So negative 3, 1. Negative 2, 2. And 1, 3. And it looks like that. Notice it stops here, right? I didn't write anything before that value. And the same was true over here. I didn't write anything over here. Because if I try to put anything else smaller than that, I get negatives underneath the radical. It's imaginary values. That's not going to show up on a graph that's a real number graph. That's why that happens.